So this is Module 1 for RM711 Applied Financial Analysis. So this module really takes a look at kind of an intro to the course, focusing first on the role of programming in quantitative analysis, some sampling of programming languages and what they do, and then really what we're going to get into, the heart of this is looking at some of the more advanced Excel functions as they relate to financial applications. So we're going to be working through a couple of different examples. There's a course file, an Excel file that's available for download on the class website that we'll use as our data set for a lot of these problems as we move through this module. So first, what is this course about? Really, the course is intended to be useful for anyone working as a financial engineer or in risk management, anyone who works directly with quants. It's meant to give you a solid understanding of how to effectively use technology to build financial models and how to work with large financial data sets. So the course is going to be very much hands-on. That's why it's being held in a computer lab. We're going to work together during class and through homework exercises to create models and of course strengthen the knowledge of computer programming as it's used by financial engineers and risk managers and other quants. So I know many of you won't end up programming on a regular basis, but the skill set here that we gain is intended to benefit you in some way in your career path because it will enable you to better problem solve, to be able to see things more logically, particularly from the perspective of a programmer. So really, if you can communicate well with a programmer, that's all you really need to be able to do. Understand the logic. Different computer languages come and go. The syntax will change from one language to another, but there's a lot of core concepts that are fundamental and that carry through across different programming languages. And this is really what we're trying to get at. If you can understand the structure and the logic, you'll be in good shape. So first, what are the different types of computer languages? Markup and scripting languages. These really just define the way content is displayed. One example here is HTML. All this really does is define the way content is displayed on a web page. There's other scripting languages such as PHP, JavaScript, ASP, Cold Fusion. These can handle input data from a web page and then dynamically manipulate the output of data for a web page. But, realistically, these markup and scripting languages are not technically programming languages. They don't have the ability to use logic, and so they're lacking. It's not what we need to use. So technically, in order to be considered a programming language, you must be able to use the code to build standalone software with logic and presentation. Some examples here, C++ or C hashtag here. Python is a big one in finance. Perl, Java is a big one also, and Visual Basic. There's also database languages, particularly SQL or SQL. This is structured query language. It's a common language that's often used on web pages and elsewhere to communicate with a database. You may have seen this. This is built inside of Microsoft Access. So if you use Microsoft Access at all for large data sets and databases, you can actually write SQL code inside Access if you choose to do that. So SQL allows websites to be dynamic and much more powerful because there can be a database residing on the website, on the server, that SQL can interact with and then display results onto a web page. SQL is loosely considered a programming language. It's not technically a full-fledged programming language. It does use extensive logic to input data, to draw data from, and run queries on data in an underlying database. But the downside of SQL is you cannot create standalone software. So therefore, it's not considered a full-fledged programming language. Visual Basic for applications is a limited version of Visual Basic. So it is technically a programming language that's built inside every version of Microsoft Excel, and it's actually applicable to all different Microsoft Office products. You could actually even use it inside of PowerPoint and Word as well. The limitation to VBA as opposed to VB is that VBA generally cannot be used to create a standalone program. VBA has to be run from inside a host application, namely Microsoft Excel or PowerPoint or Microsoft Word. But it can be used to control a different application once it's run from its host application. So while this is sort of a drawback that it can't create a standalone program, it can essentially get around that by starting up through the host program and then launching other programs from there. In other words, it's a very powerful language. It's going to do plenty. It can do probably more than you'd ever need to use it for. And what's nice is it's available to everyone who uses Microsoft Office products. So everyone has access to it. You will definitely have access to it on the job. So where we have to start, though, before we start actually coding in VBA, we want to spend the next few weeks covering some of the more advanced Excel functions because these are very important and you'll probably be using these functions very often in your career, maybe even more so than the VBA that we'll cover later on. So these can help you be more productive, and so we want to kind of start off here with a model, and our first example, Model 1, I want to just begin with something simple. I want to create an amortization table, and we'll try to use Excel's financial functions wherever we can as we build this model. So first thing is you want to download the first data set from the course website, and then we'll open that up in Excel. Okay, so hopefully you found the class file for Module 1. It's on our website. You just download that and open it up, and we've got several different models within this Excel file, right? So several different worksheets down here inside the workbook. And by the way, there are tons of keyboard shortcuts that some of which might be worth putting to memory. There's a link on the website as well for some of the keyboard shortcuts that are really useful. So basically what we want to start off here with is an amortization schedule. And I'll just kind of put a heading in here. I'm just going to center this across these cells. So of course to center, you can merge and center, or you can go into the Format Cells dialog box. Shortcut is Control-1 to pull up the format cells here and go to alignment. I'm choosing horizontal alignment. I'm choosing to center this across the selected area. And you notice that I had selected A1 to H1 before I did this, right? And this is all under the Format Cells alignment box here, right? Or Control-1 to bring up the menu. So just centering this horizontally across the selected region. So I've got, I'm bolding this, an amortization schedule. And let's just say that we want to come up with, let's just say we want to do this for a mortgage. Maybe it'll be a 30-year fixed mortgage, right? So I'll plug in some sort of an annual rate, right? We'll say, I don't know, maybe like 4.5%, something like that. Plugging this in as my annual rate. We'll say the number of years, the term in years. Let's say it's 30-year fixed rate mortgage. What else do we need? Well, we're going to need to know when the payments are made. What's the frequency? So, of course, this is going to be paid monthly, so there's 12 payments per year. So plugging all of this in. Now, we've also got to know, well, how much do we want to borrow? And so I'm just going to throw a number in here, but you can always mess with this later on. Let's just say, we wanted the loan amount. I don't know what's appropriate. You want to say 300,000? Plugging in 300,000 here. I'll just change the formatting style. Make this, maybe I'll even keep the, well, that's fine, 300,000, right? So what I want to do is figure out based on these values, what would the monthly mortgage payment be? And of course, there is a mathematical equation you can use that you must have learned in a corporate finance class, right? But there's also an Excel function that we can employ. So what is the payment? That's what we want to figure out, right? In this case, it's a monthly payment. What is it? Well, we can use the PMT function, the equals PMT, right? Equals PMT, and what I can do is, of course, you can open parenthesis and you'll see the arguments pop up underneath, or you can use equals PMT and then go Control A to bring up the function arguments, right? You could also get there by saying equals PMT, open parenthesis, and just clicking on this little FX up here. That'll bring up the function arguments as well, right? So what I want to do is plug in the rate. Now I'm going to take the annual rate and I'm going to divide it by the frequency. So what this looks like, it's the annual rate divided by 12 gets me to, kind of a periodic rate, a monthly rate in here. Next, it's asking for the number of periods. This is really the number of payments over the life of the loan. So in this case, we have 30 years, but there's going to be 12 payments each year. So 30 times 12 gets me 360 payments, right? Total number of payments for the loan. And so the loan amount is next, $300,000. That's going to go in as a present value. We're borrowing that amount today, and we're going to pay it off so that in the future, there will be nothing left on the loan. So the future value here would be 0. Present value is going to be $300,000, right? And the type, if you've seen this before, the type is referring to whether this is an ordinary annuity or an annuity due, right? In the case of an ordinary annuity, we're talking about the first payment happening at the end of the period, which is normally what you'd see. For the type, we can say 0 or leave it blank. That would be an ordinary annuity. If instead the payment is happening immediately, you would change the type to 1, and that's going to change your result, you see here. So if I were signing my closing, if I were at my closing for my house, and I made my first payment immediately at the closing table, then the type would be 1. But in reality, what happens is you sit down at the closing table, you sign a bunch of papers, you buy the house, but then your first mortgage payment happens 1 month later, right? Or on some designated date in the future. So the type would be blank, 0, ordinary annuity. So I'm going to go ahead and hit OK, and you can see that we have monthly payments of $1,520.06, right? And because we use that built-in function, and our present value is positive, we're getting a negative monthly payment amount, just indicating that these payments would go out, right? We have an inflow of $300,000, so we have to have outflows of $1,520.06 every month, right? Nothing to be alarmed about. It's just the way Excel displays cash inflows and cash outflows, right? Similar to a financial calculator. So what I want to do next is, well, I guess first, let's ask ourselves, when is the first payment going to happen? First payment date. And this could really be any date that you want to plug in, but let me just say I'll use September 1st, 2017. So plugging in this date, and so now I can kind of set up my amortization schedule. What I'm going to want to plug in here is first, I guess, the payment number. And then I'll say, okay, well, based on that payment number, what's the payment date? So here, I guess what I could do is just kind of plug in the number 1, the number 2, right? So ultimately, I'm going to have 360 payments on this loan. Now, of course, what I could do is kind of, I could make this 1 plus 1, right? I could take 11 plus 1, and then I could copy that formula down, right? And it'll keep increasing by 1. That's one way to go. Right? We could also do something like the autofill, where you type in 1, then you type in 2, and you select these these two items and use the autofill handle, this little box in the corner. This works for copy paste, but it also works when you have data as part of a series. So 1, 2, and then this will recognize that as a series and it will carry the series forward 3, 4, 5, 6, and so on, right? So however you want to do this, basically I just want to copy this all the way down, use an autofill so that I get down to 360 payments and I'll just stop there. Right, we know there's going to be 360 payments on this. So we'll just stop there, right? Got 360 payments. So next we're asking what's the payment date? Well, we know that the first payment's going to happen on September 1st. What about the next date? How can we figure that out? Well, there's actually several ways you can go, but I guess probably the best way to go about this is to use a date function. Excel has quite a few date functions built in, and these can be very helpful, particularly when you're dealing with any sort of dates. If you're trying to calculate pay periods, or you're trying to calculate coupon payment dates, or dividend dates, or whatever it might be, you can use these built-in functions. What I'm thinking of here is the eDate function for ending date. And so what I would do here, again, Control A will bring up this dialog box. Here, if you use this, you just have to say, okay, well, what's the starting date? And I guess really what I could do is set the starting date equal to that first payment date. And I'll lock that in. And then what I can do is tell it to move that date into the future. In this case, I'm going to use the payment number for the prior payment number. This way it advances it by just 1 month. Right? I'll leave this as a relative reference so that when I copy down, the reference to B8 is locked in, right? I hit F4, the function for key, to add the dollar signs on that. So that locks that down. It's going to advance it by 1 month, leaving me with a date of, well, it's hard to tell that that's a date, right? But if we use the date format, you'll see that in fact that is a date, October 1st, right? Excel assigns every date a serial number, and that corresponds to a particular date. It's useful because then you can actually move dates forward and backward using these date functions. So what I can do now is just double click on this autofill handle, right? Just getting it right there. Of course, you could also use Control C, Control V, Control D to copy down, but I'll just double click on this and it should carry that forward so that you can see by the end of this thing, the final payment in this case is August 1st, 2047, right? 30 years out. Yeah. So what else do we have to plug in? Well, I guess we could plug in the beginning balance. Maybe I'll even do it like this. Beginning balance on the loan. What's the beginning balance on the loan? Well, it's going to start off at $300,000. Right? $300,000 is the initial balance. Then we need to know, well, what was the monthly payment? Maybe I should do it this way here. Let's see. And so I'm just going to leave it in here as 1520.06, right? We'll say that each payment is just that minimum payment of 1520.06. Now this amortization schedule has the flexibility to, if you wanted to pay more than the minimum, you could do that and the amortization schedule would adjust. But let's just say for now, we'll leave this in as 1520.06. Maybe what I'll do is negate this. So equals negative B7. This way, it'll show up as a positive value. Doesn't really matter. It's just, later how we want to calculate the rest of this. So equals negative B7. I'm going to lock this down with the F4 key. Again, just locking that down, making it an anchored reference or an absolute cell reference. This way I'll be able to copy it down later. What else? So we got the monthly payment. Now, there's a couple of other pieces we can plug in here. So the next thing you might want to do is calculate how much interest, how much of the monthly payment here is going towards interest, and how much is going towards principal. And once we figure that out, we can see what the ending balance is on the loan. Now, there's a few ways you could calculate the interest and principal. I mean, one way is to kind of manually do this, right? But there's also some built-in Excel functions that would do this for you. Now, if you were to calculate the interest on this, what you'd be doing is taking the beginning balance and multiplying it by the annual rate divided by the frequency, right? And that would give you the interest portion of the payment, right? So that's one way to go about this. And of course, you'd have to lock down the proper references before you copy this down. And then once you had the interest portion, you could just take the monthly payment minus the interest to see how much is going towards principal, right? $395.06. So these are one way to do this, right? This is kind of the mathematical way to do it. But I wanted to show you these financial equations that we can use as well, the financial functions. So for the interest portion of a payment, there's IPMT, interest portion of a payment. And this looks a bit like those other, payment function or the other time value of money functions. What you'd have to do here is plug in the rate. So you'd plug in that 4.5%, I'll lock that in, dividing that by 12, by the frequency, again, locking that in. PER is the payment number, right? Which payment number, which period are you in? So you'd have to use this here, and you'd want to leave that as a relative reference, right? Everything else is going to be locked in. So NPER is the total number of payment periods. That would be 30, locking that in, times 12, locking that in. And the present value would be the loan amount, $300,000, locking that in as well. So the only thing that's a relative reference here is the payment number, right? That's going to change as we copy this down. And so you can see we get the same answer. It's just this time, if you've used the built-in function, it shows up as a negative value, cash outflow. If you don't want to see that, and I probably don't want to see that here, so I'll just negate the whole thing, equals negative IPMT. So that's going to give me that 1125, right? Just looking at this one more time, same thing we got before, right? Equals negative IPMT, and then you walk through that function. Now, there's also a principal portion, PPMT, right? Of course, again, we could just subtract the two, the monthly payment minus the interest portion, but if you wanted to use this PPMT, you're welcome to do that as well. PPMT, again, just taking the rate, locking that in, dividing by the frequency, locking that in. PER is the payment number, pulling that in from here and leaving it as a relative reference. NPER is going to be the number of years times the frequency. Again, locking both of those references in. And present value is the loan amount, locking that in as well. So you can see that the principal portion of the payment, $395.06. And again, it's showing up as a cash outflow, a negative. So if you want to remove that, make it positive, equals negative PPMT, right? Just plugging in that negative sign there, it's going to get you a positive answer for the principal. So now you can figure out the ending balance. It's just going to be the beginning balance minus the principal that got paid off. So you're left with a balance of $299,604.95. And that is the number that's going to carry over to start the beginning balance in the next period. Right? Just pulling that in over here. Right? I'm getting these hashtags just indicating that the column is not wide enough. So just widening that up. right? And of course the formatting, if you want this to look uniform, a quick way is to use this paintbrush format painter, right? So if you like the formatting on this one, click on it, click the format painter. It looks like it's going to copy it, but it's only going to copy the formatting. So now all I have to do is click on the cell that I want to apply the formatting to, and it will quickly apply that same formatting style. So now all I've got to do is carry these all down. So copying this down, just double clicking, and then doing the same on all of these. Once these are all completed, you should see the table looking like this. So what's happening is the balance is declining, right? Monthly payments staying the same each period. Interest, the amount of the payment that's going towards interest is declining because over time you have less and less of a balance to earn interest on. The amount of the payment that's going towards principal is increasing over time. And so by the end of this whole thing, if you jump down to the bottom, you'll see that at the end, here if I widen up this column, at the end, we have a zero balance, right? With that 360th payment, we have paid off the loan completely. So that's the logic here. Now, you can at any point pay more than the minimum payment, and you can just kind of mess around with this if you want, just making any of these numbers different to see that you'd be paying off that loan quicker and to see how that affects the amortization and the time it takes to pay the loan. But nevertheless, I'm going to just leave this as is, right? Hopefully you were able to solve for each of these, right? Of course, if you wanted to, you could go further on this and you can, I'm just kind of going over each of these. What you can do is, right, this pulls in the ending balance. If you wanted to, you could plot this, say maybe in a in some sort of a graph in a chart. Maybe if I wanted to plot the beginning balance, I could select this range and just go ahead and insert a chart, right? Even just something like a line chart, for example, just a simple 2D line chart. And we should see something like this, right? Where over time the balance is declining, and it's actually declining quickly as we approach the end. Now you kind of see this this concave graph, right? So yeah, so I guess what I'll do is just kind of leave it at that for this first model. Let me move this out of the way. All right. So let's stop there and go back to the notes. In the next Excel model, model number 2, we're going to use some of Excel's statistical functions to evaluate stock prices and returns. But before we start doing that, we should quickly review the measurement of risk and return as we'll use it in this context. The prices of most assets traded in competitive markets have distributions that are approximately log normal. For the time being, we'll assume that each stock's future price is indeed log normal. When a stock price is log normal, its return will be normal if and only if we measure return on a continuously compounded basis. Many people ignore this fact or gloss over it and instead measure return on a discrete basis and treat return as though it's normally distributed, even though it's not, right? And you've probably done this. You've probably measured returns as HPR, holding period return, just discrete returns. That's typically how we do this at an undergraduate level. But here, throughout risk management and risk measurement courses, we'll be measuring returns on a continuous basis. And that's justification to treat returns as normally distributed random variables. And this is going to be very important when we try to calculate the value at risk and other risk metrics. So that's why we mention it here. We'll talk about how you can calculate these continuously compounded returns. Really, it's just a different way of looking at return. Instead of return that is just compounded once per year, discrete returns. Here we look at it as if it's being compounded continuously throughout the year or throughout the time frame. Basically, you're earning interest every millisecond, if you will, right? That's the logic here. So since we're going to be dealing here with stock returns, we want to recognize that there are actually two components. One is the change in price, and the other piece is the dividends that we receive. So the return includes the gain, capital gain or loss, from a price change, plus the dividend component from dividends that are paid out by the company. We can measure the return series over any differencing intervals you like, days, weeks, months, quarters, or years. It's most common in portfolio theory and usually in portfolio management practice to measure returns on an annual basis, just for simple comparison. But that doesn't mean that the raw data was indeed annual data. Instead, the raw data could have been from much shorter periods. It could have even been, daily, and then annualized. And when you're measuring returns on a continuously compounded basis, it's very easy to go from any time interval to an annual interval or vice versa. So that's one of the nice properties of continuous returns. First, let's begin by generating a dividend-adjusted price series. This is simply the price, along with any dividends that have been paid. We'll add those back to the price. So here, let's use some daily price data to demonstrate the process. Here by daily price data, we mean closing price data for each trading day. And there are 252 trading days in a given year. So suppose as an example, we pick December 31st, 2010 as our starting point, and we pick a stock whose closing price on that date was $34.51. Moving forward, the next trading day is January 3rd, 2011. Suppose the closing price on that date was $35.21. There were no dividends paid on that day. And the following series illustrates the calculations. So we have days, we're marching forward through time, the raw closing prices on those days, and the dividends that were paid. Now, notice that some of these were hidden. There was at some point a dividend that was paid because here we're calculating the cumulative dividend over time. You can see that ultimately over the course of the year, $1 was paid out in dividends. So the dividend adjusted price over here is the raw closing price plus all of the accumulated dividends up to that point, right? So you've probably seen this if you've looked at like Yahoo or Bloomberg and you look at the closing price along with the adjusted closing price. That adjustment is for dividends and other stock splits and that kind of thing. So, yeah. The next thing that you'd want to do here to calculate the continuously compounded return is to take the natural log, right, the ln function in Excel is what's used, and then take the ending stock price, right, the ending adjusted price, over the beginning stock price. And so in this case here, what you'd be doing to get this result, you'd be taking the natural log of the ending price over the beginning price. So 35.21 over 34.51 generates a continuous return of 2.02% over that 1 day period. And you do the same, you just copy that down for the rest of these. Once you have those continuous returns, you could then compute the mean periodic return, right? The average, and you can also calculate the standard deviation of the periodic return. For standard deviation, you can use the STDEV function is for a sample, and actually here we are using sample data throughout finance. You'd be looking at sample data, so STDEV or STDEV.S for sample. There are other functions, STDEV.P for a true population, but this is not a true population, so we wouldn't want to use that in this case. So we would want to calculate these periodic mean and periodic standard deviation using those functions. Then once we have the periodic mean and periodic standard deviation, right, since the raw data was daily data, this is actually the daily mean and daily standard deviation, you could then annualize that. And the way to do that, it's very simple if you're using continuous returns. The annualized mean, you would just take the periodic mean times n, where n is the frequency. So if we were using a daily mean, we would use 252 for n, right? If it were monthly, we would use 12 months in a year. If it were quarterly, we'd use 4, and so on. When you're annualizing the standard deviation, what you would do is take the periodic standard deviation and use the square root of n and just multiply those two pieces together. So in this case, it's a daily data, so we use the square root of 252 times that daily standard deviation. So that will give you an annualized mean and standard deviation on the return. So looking here at Model 2, you can see I've got some prices for the S&P, and we've got some prices for IBM. Now these have already been adjusted for dividends. So what we want to do is calculate the monthly returns. Now these are monthly prices, so we can calculate the monthly return on a continuously compounded basis. And you can see the time here is moving forward. So what we want to do is use the natural log function, the ln function, take the ending price here in February 2004 over the beginning price, January 2004. And so that's going to give us our continuously compounded monthly return. You can see that the price increased. We have a positive return of 1.21% over that 1 month period. I'm just going to go ahead and copy that down, just again using this autofill handle. If I just double click, it's going to copy it all the way down to the end. So we have like roughly, roughly 10 years worth of data here. So what I want to do now is, let me just minimize this. I want to do the same thing here for IBM. I could actually even copy this, right? I could copy this here, Control C, and then I would just paste it over here. And of course, you're going to see that calculate on the same way as it did before. So now I've got these returns here. And if I wanted to go ahead and calculate the periodic mean for the S&P, it's just going to be an average, right? Equals average. I'm going to use the average of these monthly returns that we have here. So selecting from C3 down to the end, right? I'm quickly using, Shift Control and the down arrow key to jump to the end here. So C3 to C121 gets me an average monthly return for the S&P of 0.413%. Periodic standard deviation is going to be equals STDEV, right? Or STDEV.S. So this one, STDEV, you can see it's based on a sample, or STDEV.S. Either way, so I'm going to go ahead and select that same range from C3 to C121. Gets me a standard deviation of 4.312%. Right, and then I'll do the same thing for IBM. So the average gets me to the periodic mean, selecting G3 to G121. Looks like this, 0.664% equals STDEV.S for the sample standard deviation on IBM. Again, G3 to G121, 5.43%, just to look at this. So what we want to do, now we have monthly mean and monthly standard deviation, we want to annualize this. So we said for the mean, all you have to do is take the periodic and multiply it by the frequency. Now in this case, the data is monthly. So there's 12 months per year, so I'm just multiplying by 12. For the standard deviation, we would take the periodic, the monthly standard deviation, and multiply by the square root, SQRT, of 12, right? SQRT function, or you can take 12 raised to half, right? Raised to 0.5. So annualizing these, it looks like this, right? I'll copy this and paste it down here. So you can see we end up with results that look like this. So we've gotten to this point, and so now we've calculated the annual equivalence of the mean and standard deviation. And as a side note, the annual mean and standard deviation of return obtained in this way are historical, right? We're looking backward. And there are ways to obtain forward-looking means and standard deviations as well. And some people think that these are more indicative of future performance. So we will be exploring those down the road. So suppose, as in our example, we have two periodic return series, one for each of two stocks. For the matched data points, right, the returns at the same periods in time, we can calculate the covariance between the two returns and the correlation between the two return series. And covariances calculated from a non-annual periodic return series would not be annual unless you took another step to annualize them. Whereas correlations calculated from periodic return series can be treated like annual correlations because correlations are independent of the length of period used to measure returns. So for correlation, we don't have to do anything to annualize it. For the covariance, you'd be taking the periodic covariance and multiplying by n, by 12 if it's monthly, or by 252 if it's annual. So what we want to do, jumping back to our Excel file, so now we just want to go ahead and calculate the covariance. And of course, there's a lengthy way you can do this by hand, but we're going to make use of the functions that are available to us, right? Now, covariance.p is for population. Covar is also for a population. So what we want to do here is use covariance.s for a sample. Covariance.s, and what we'll do is select both of these arrays, both of these ranges. So first using the S&P returns, and next using the IBM returns. Now it doesn't matter which order you choose these in. It looks like this. So we're using those two return series, right? If you want to pull it up in the arguments, C3 to C121 as one array and G3 to G121 as a second array. Again, it doesn't matter which order you put these in as long as the two series are of the same size. So on a periodic basis, the covariance is 0.14%. To annualize this, we would take that periodic, that monthly covariance, and multiply by 12 since this data is monthly. That's going to get us a value of 1.68% roughly. The problem with covariance is it has no dimension, right? We know that there's a positive relationship between these two variables, but we don't know how strong the relationship is, which is why we take it to the next step and calculate the correlation. Here, correl is the function we can use, and again, we just select the two arrays. So selecting the returns for the S&P and selecting the returns for IBM. And so now you can see a bit more. There's roughly a 60% correlation. So if one stock moves up, you'd expect the other stock to move in the same direction with a roughly 60% of the time or 60% relationship there. So if one moves up by 10%, maybe the other would move up by 6%, at least historically. So far, that's where we're at. So we've gotten this far. Now, there are a few other things I want to take a look at since we have this data set here. One is, let's try using some of the statistical functions for databases. And this is going to allow us to calculate the average return or variance or standard deviation of just certain returns. And there's actually all sorts of things you can do. So, I mean, you may have seen things like the count if, sum if, average if functions. Those are useful, but there are some additional functions that people don't use that often. They're called the database functions. And they're a bit more robust in some ways. So let's take a look at this in a couple of ways. So the first thing I want to do is bring in the headings. These headings, it's absolutely crucial that the headings match the data set. So for example, let's say we want to isolate we'll look at the S&P returns. Maybe we want to calculate the mean return when you had, I don't know, maybe negative returns. So first thing I would do is pull in the headings. I'm just going to use a formula here to pull in the heading with the date. I'll copy this across, right? So the date, the S&P adjusted closing prices, and the continuous monthly return. Let's say that I want to focus on just the returns that are less than 0, right? Something like that. What I can do now is use the function, the database function, d-average. This is going to allow me to calculate the average just within the conditions that we specify. So d-average, here it's asking first, what's the database? And so that's going to be this section here, right? We're going to be looking at the S&P, selecting from A1 to C, I'm selecting this whole area, A1 to C121. The field is focused on which one do you want to output? What do you want to calculate the average of? Well, that's actually in the third column. So 1, 2, 3, right? The returns are in the third column. So the field is going to be field number 3. And then for the criteria, here, what I'll do is jump back up. For the criteria, we're going to have to specify that this is the criteria. All right, this area here that contains our headings and the specific rules, the specific conditions. So I've plugged in less than 0, meaning that we want to just focus on the negative returns. And it turns out if you look at just the negative returns, the average was negative 3.799%. That's an average monthly return. Pretty substantial there when you focus on just the negative returns, right? And by the way, you can change this on the fly, which is nice. So if I wanted to instead maybe look at those returns that are greater than 5%, you can see that the average of those greater than 5% was 7.239%. You know, something like that. So you can have lots of good stuff in here. You can mess around with it. What's nice about these database functions, there's actually quite a few. D-average is one, but you've also got D-count, D-standard deviation is what I was thinking of next. Sum, of course, but D-STDEV is going to work for us here for a sample, and it works the same way. So again, the database would be the data that you want to focus on, so that is this data here from A1 to C121. Field is what do we want the standard deviation of? The third field contains the returns. We want to calculate the standard deviation on returns. So I'm using field number 3. And then for the criteria, we're going to want to use the criteria that we specified over here. So L3 to N4, right? The headings as well as the specific criteria. So when we look at those returns that were negative, we have standard deviation on those of 3.74%, right? And again, you can kind of mess with this if you want. Maybe I want to look at greater than 3%. Greater than 3%, and just kind of see how that looks. The possibilities are endless here. Yeah, what I had in mind here is what if we wanted to maybe look at IBM's returns but only focused on a particular year? Well, for that, you'd have to change this data just a little bit, right? What we'd have to do is extract the year from the date so that we'd have this as one of our criteria, right? So that we'd have the year available to us. But we can do that, right? There's a simple function we can use to extract the year from a date. It's actually the year function. So if you just use a year function and select a particular date that you already have in your spreadsheet, this is just going to give us the year, 2004. I can copy this down and you'll see 2005, 2006, and so on. So the year function is a simple date function that works. So again, what we can do here for the database functions, set it up so that we're pulling in those headings. Here, focusing on the year in cell E1. And I'll copy this across. Year, and then IBM's adjusted closing prices, and the returns for IBM. So again, what we can do is use these database functions. But first, let's say I want to look at just one particular year. You know, maybe I want to look at 2008, right? Pretty awful year for the markets. The periodic mean, what was the average return during that year? Well, D average. And again, the database here is going to be IBM's data. So selecting from E1 down to G121, field is going to be field number 3. The third column contains the returns. And for the criteria, again, we're going to look at these headings. So this section here, L12 to N13. Right, so for 2008, it looked like the average monthly return was almost -2%. And that's a monthly return. Pretty horrendous, right? If I look at, 2006, you can see it was a positive return, significantly different. If it's 2009, geez, 3.8, significantly high there. 2010. So you can kind of look at each of these. Let's say we leave it at 2008, right? Pretty horrible year. And again, if you wanted to use DSTDEV for the standard deviation, same deal. Just going to jump up here and select our range, E1 to G121. Field is 3, and criteria is again going to be this section that contains all the criteria, L12 to N13. So here you can see that during that year we had a lot of volatility, right? Very high monthly standard deviation and low monthly returns, right? This is different if we kind of play with the numbers here, Cool. Now, there are a bunch of other interesting statistical functions available here that I thought I could mention. What if we want to know some details about the S&P 500 returns in this series? What if you wanted to know the largest return? Well, of course, that's easy, right? We can use the max function for the maximum. But what about the second largest? Well, for that, you'd have to use the large function. And this actually gives you the option, which value do you want? So if we're looking at the S&P returns, I'll select that range of S&P returns, right? Again, just pulling this in from here, C3 to C121. K in the function here, K is asking which value do you want? Do you want the first largest? Do you want the second largest? And of course, in this case, I've chosen the second largest. So that's giving me 8.98%. That is the second largest monthly return in this data series, right? If I plug in a 1, it's going to give me the first largest. So the max, it's giving me what the max function would give me. If it's the third, well, of course, it's going to be a little less, right? Fourth, fifth, and so on. And there's also a small function, by the way, which does the same thing, just gives you the smallest instead of the largest. So some other ones, what if I had a specific, you can see this is a very specific monthly return. What if I wanted to know where does that rank in our list, in our set, in our series of returns? We can use a rank function here to figure that out. And so first it's asking, what is the specific value that you're looking for? Well, you're looking for this return within the reference data, which is the S&P returns, right, which are over here, C3 to C121. And then this last one, the order is just saying, okay, well, you know, if you want this sorted descending, you'd plug in 0 or leave it blank. Or if you want ascending, leave it, you know, plug in any number here. So if I plug in a 1, it's gonna rank it smallest to largest. If I leave it at blank, it's gonna give it largest to smallest. So basically this is telling me that the return of 5.5779% is the 9th largest, the 9th from the top, right? If we wanted the same but from the bottom, well, again, we would just say, okay, the specific number is this one here. We're looking for that in the series of S&P returns, which is over here, C3 to C121. This time the order would be, you plug in any number. Say I plug in a 1, it's going to give me 111th, right? So in other words, there's 120 data points. This ranks 9th from the top or 111th from the bottom. Yeah. Now I'm thinking we keep looking at these S&P returns. It might actually be helpful to name the range of S&P returns. This way we don't have to keep kind of scrolling back and forth and selecting that range over and over again. So if you wanted to name this range of S&P returns, right, what we could do, so over here, just select that range, just selecting that whole range, and just go into that name box over here and just give it a name. Now, it's not going to like SP500 because that's actually a cell reference. So we could go with just SP. SP would be good, or if you wanted to write out Standard Poor's, something like that. There's no spaces allowed in a name, so oftentimes people use an underscore instead of a space. I'll leave it at SP here, just hitting enter on this. So now we've got that named range. And by the way, if you wanted to, you can go into the formulas name manager. That's going to give you a list of all the named ranges. And you can make any changes, delete names, edit names in that name manager as well. So let's use that name now going forward. So here, what if I wanted to know which return ranks above 50%? You could use this percentile. And for this one, the array, you could select the range of S&P returns, or we could just type in SP since we named the range. Then K is just going to be whatever percentile rank. And so this tells me that a return of 1.2% ranks above 50% of the other S&P returns, right? In other words, if I wanted to know what is the top percentile or the top, this is telling me that 10.23% is above 100% of the returns, right? 0 would be the lowest return in there. And so anything in between, 50% is kind of like the median there. And then this one, percent rank, is actually going to give me the opposite. If I have a specific return that I'm looking for and I want to know what percentile does it rank at, we can use percent rank. And again, SP is the array. X would be the specific return that we're looking for. Significance is just how many decimals you want to bring this out to, so I'll leave that blank. So this tells me that a return of negative 3.48922% ranks above only 13.5% of all returns. So it's pretty near the bottom. Now, just a couple of other tools. You may have seen some of these before, but if I wanted to know how many times we have a negative return, we could use a COUNTIF equals COUNTIF. The range would be the S&P, right, that named range. Criteria is, well, in this case, we want to know how many times the return is negative. So we're going to say less than 0. And what we'd have to do is just plug this inside quotes, right? So quote negative, or quote less than 0, close the quote. And it says here that out of 120, 44 times were negative, right? 44 returns of the 120 were negative. And then you could go further. You could say, well, what was the average if? And you notice there's also plural of these. Average if is, so we'll say S&P, criteria is less than 0. And so by default, it's going to average the S&P returns unless you tell it otherwise. So I'm going to leave that blank, or I could just put in SP again, but it's not necessary. So you can see when there was a loss, the average was negative 3.8%. Right? I think that's what we came up with earlier with the d-average function as well. So these are just some other tools to kind of get a good summary of what's going on with your data set. So just jumping back to the notes here, we went through a bunch of these different statistical tools. I want to move over to model number 3, and this gets into using some of Excel's regression analysis tools to evaluate the relationship between two variables, in this case, of course, IBM and the S&P. So before we get into these tools, we want to just briefly review regression analysis. Right here, we're talking about multivariate statistics. Right, regression analysis is really a method of determining the functional relationship between two random variables from a multivariate data set. If that relationship is linear, then we try to fit a linear equation to the data, and this is what we refer to as linear regression. Right? And so with financial data, regression analysis can be used to estimate a stock's beta coefficient. The beta coefficient is a key measure of systematic risk in the stock market. And what you would be doing is looking at the return on a particular stock of your choice related to the return on the S&P. Now, technically, if you're calculating the beta, you'd want to use the return in excess of the risk-free rate for both of these. But nevertheless, people often just go ahead and use the percent return as well. So with regression analysis, there is a dependent variable, also called the regressor variable. This is the variable whose variation is explained by other variables. There's also the independent variables, or the explanatory variables, and these are the ones that are used to explain the variation of the regressor variable. So what you have to look at is sort of which variables are independent and what is it that you're trying to predict? What's dependent on those independent variables? In our case, if we're looking at the S&P, this would be the independent variable. The S&P, we'd say, well, we don't have any control over that. The S&P is going to do what it's going to do, and we want to see how the S&P impacts IBM. So IBM would be the Y variable, or the dependent variable. IBM is dependent upon the fluctuation in the S&P, right? At least that's the assumption here. So once you've got this, once you've run this regression, you can then use your output to form an equation, right? And so, of course, you've got you're solving for the return on IBM, in this case, Y. It's equal to an intercept term plus B, the slope, right? And B is going to be our beta, times X, where X is whatever you think the S&P is going to return, right? The return on S&P. And of course, there is always some error term because this is an equation that we're estimating. We're using this as an estimate, so you're never going to get it right 100% of the time. So there are functions on this in Excel. Now, I want to use this. There's actually an add-in, the Analysis Tool Pack add-in that we can use to run regressions in Excel. You've probably also done this in another statistical tool pack like SAS or SPSS or R. There's lots of different software out there for this. But let's try this in Excel. So turning back to this Excel file, here in Model 3, what I want to do is just pull in some returns from our Model 2. So basically, I'm just going to say, all right, let's set this. I guess first, let's take a look. What do we have here? In Model 2, we've got the dates, and then we've got the S&P and IBM returns. So let me just put some headings in here. The date, the S&P, and IBM. So what we're going to do is pull in the returns. Now, I'll just do that with a formula equals, jumping back to Model 2, pulling in. Now I'm going to pull in the date for February since that's really the first return we have. So February 2nd, 2004, just hitting enter on this, pulls it back in here. Now pulling in the return for the S&P on that date from C3. And I'll do the same for IBM equals, pulling it in from G3. So what we want to do is pull in all of the returns and dates all the way out. So I guess we got to go down to like row, I guess, around 120. What did we say? Yeah, it looks like row 120. Right? If we go any further than that, we get some weird results, right? So we pull it in from, all the way down to row 120. That pulls in all the data. So now we've got the dates, we've got the returns on the S&P, and we've got the returns on IBM, right? Just pulling those in. And so what I want to do is run a regression on this to see what the relationship looks like here. And so what you'd have to do first is make sure that you have the Analysis Tool Pack, which is available in the Data tab. You'll see Data Analysis if you have that installed. Another good one is the Solver Tool Pack. These are both very good, but these are both add-ins that must be installed if they aren't already. So if you don't have those, what you've got to do is just go up to File and then the Excel options. So File Options, and in here, you'll see add-ins on the left. So if you click on add-ins, so File Options, add-ins, you then have to click this Go button over here, Manage Excel Add-ins, hit Go, and that's going to give you a list of all of the potential add-ins that you can install. So depending on the way Office was installed on this computer, you might have to put an Office CD in to get this to install properly. But oftentimes you don't have to do that. So in my case, Analysis Tool Pack is on here. Solver, or in my case it says, looks like it's a French spelling here, Complement Solver. So I'm checking Analysis Tool Pack. If you want, you can also check the Solver Tool Pack. You might even have some additional add-ins available as well. But here I'm just checking these two, hitting OK. Once you hit OK, it should install those, so you'll see them now under Data on the right-hand side. Once you've got that in here, you can go ahead and use the Data Analysis tool. And by the way, these add-ins were all created using VBA, and then they can be saved as an add-in. So that's something to keep in mind too if you ever decide you want to build an add-in. Nevertheless, here in this case, what we want to do is run a regression. So that's one of the options here in the Data Analysis tool. Hitting OK. And so it's going to ask me for the Y range and the X range. And with this regression tool, you are allowed to select labels, the headings on top. So generally, I try to do that because it makes it easier later for the interpretation. So what I'll do is select the Y range. Now we said our Y variable, is IBM in this case. This is what we're trying to predict the behavior of. It's dependent upon the S&P's behavior. So for the Y range, I'm going to go ahead and select, I'm including the label C1 down to C120. And for the X range, I'm going to choose the independent variable or variables if you have more than one. In this case, it's the S&P returns. And again, I'm selecting the labels. If you do that for one variable, you have to do it for all. So B1 to B120, I will check the labels box since I did include labels. Now there are lots of other options in here. One that might be nice is to show the line fit plot. That's kind of nice. It's just going to display a graph, to see how good the model looks. And so, yeah, I'm going to go ahead. I can put this in a new worksheet. That's fine. I'm just going to hit OK. So this should run the regression quickly, and it's going to give you some output. So first, you can see, if you did check that box for the line plot, you'll see what it looks like. You can see what was predicted based on the regression is this red line. And you can see what the actual IBM returns were, which of course it's not fitting perfectly on the line. But nevertheless, it's trying to fit that line as tightly through the points as possible. And so, basically here we've got, the output from the regression tool. And so important pieces would be, things like the coefficients, right? This is what would be used to form the equation. This 0.75 is the slope. And actually, in this case, because we ran IBM against the S&P, this is actually IBM's beta. And then we have a coefficient, 0.003. There's some other values, things like the R squared or the adjusted R squared, indicate how good the model is. You can see these numbers are very low. We want numbers close to 1. These are, basically indicating that only 35% of the variation in IBM can be predicted through the variation of the S&P. So it's not a very good model. That's sort of typical for financial data. It's not unusual to see R squareds of like 35%. And then there's some other items too, like the significance F and the p-values. These are all, close to 0. So we'd say that those are good indicators that the S&P is a good predictor of IBM. And, kind of loosely discussing this, but I'm sure you've gotten into this in much greater detail in an econometrics or a business statistics class. So anyway, this is the regression output. I'll just rename the sheet. But there are some additional tools that can be used to get at some of these key pieces of information without having to run the full regression. So, there are some functions. One is to go ahead and use, if you wanted just the slope, right? You could use the slope function. So you'd see you just have to plug in your Y variables, which would be IBM's returns. Now here you can't choose the labels. And then you would choose your X values. And of course, that's going to get you to the same slope that we saw when we ran the full-on regression. So roughly 0.75. There are similar functions as well, like the intercept and the R squared. Intercept is equals intercept, not surprisingly. So here, again, the Y's would be IBM returns, and the X's would be the S&P returns. And again, this is just a way to get at that intercept that we saw from the full regression. The R squared is RSQ. That's going to give you the RSQ, R squared, plugging in the Y variables, or the Y's, and then the X's. So again, gives me the R squared right around 35%, 36%. And by the way, there is one other way you could get at all this data, and that is there's actually an array function that can be used to do this as well. It's called the the linest function is what it's called. Now, I just copied some of this information in here because the linest function is a line estimator function. It will give you all the data from a regression output, except without having to run the regression. It gives it to you in a nice format, but it's an array function. So the way this works, you select 10 cells. Now, you don't have to have this information here. I just kind of plugged it in so it'd be easier for you to interpret this. So I'm selecting 10 cells, and then equals linest. And again, it's going to ask me for the Y variables, IBM's returns, the X variables, so that's going to be the S&P's returns. Constant is whether or not you want an intercept. Now, if I'm going to leave it blank so that we do get an intercept term, so it's not crossing through the origin. And then stats is true to give me all 10 statistics from the regression. Now, the trick here, though, because this is what we call an array function, it's working on series instead of single cells, and it's going to output to more than one cell. So you can't just hit OK, because if you do that, it's going to give you just one piece of data. What you need to do is select the whole range, write the linest function, and then use Control. Here, I'll pull this up. It's fine if you have the box up, but you just want to hit, instead of OK, Control, Shift, Enter. That's going to output results to all 10 cells. It's going to give you all 10 pieces of data. And this is why I've given you the interpretation next to it. So we've got the slope, we've got the intercept, we've got the standard error, the R squared, the F statistic, degrees of freedom, standard error, all sorts of good information here. You can find this information and more about this in Excel's help related to the linest function. So again, these are some interesting tools to keep in mind in case you have a need for forecasting or need for linear models like this to determine some sort of a trend and use it to predict things going forward. So just jumping back to the notes here, we were able to run the regression. We saw what that looked like. We were able to form an equation using the intercept term here plus the slope times the expected return on the S&P. Now, if you plug in some number for the upcoming return on the S&P, you'd have an expected return for IBM. And again, we said the beta, in this case, the beta is the slope, and that's a useful measure of systematic risk. So the last model here, model 4, talks about if statements, if functions, as well as lookup functions, which are very, very useful. Specifically here, we'll be looking at the VLOOKUP, vertical lookup, where you have a table structured this way, and you're going to look vertically down through the data to come up with a result. So what I've got is a table with some income tax rates, and the way to interpret this is if your income falls between $0 and $10,000, you would have to pay just a flat 10% tax rate. Imagine. If your income is between $10,000 and $37,000, you'd pay 15%. If it's between $37,000 and $90,000, you'd pay 25%. And so on. So that if your income is above $407,000, you'd pay 39.6%. Now note, you'd sort of have to set up a table kind of in this fashion, where, between these two boundaries goes here, between these two boundaries goes here, and so on, in order to get a VLOOKUP to work with this type of data. But let's first work through this with an if statement to see what that would look like. Basically, what I'm trying to do is if I plug in some income level, I want to calculate what the tax rate would be for that income level. Now, it's going to be a nightmare with an if statement. I don't know if you've used these if statements before. It tests for some logical condition. If the outcome is true, it's going to output some result. If it's false, it's going to output some other result. Now, the problem here is that we have more than 2 potential outcomes, right? There are, I guess there's 7 potential outcomes here, different tax rates that could be applied. So yeah, that's going to make this very complicated because we're going to have to nest one if inside another if, inside another if, inside another if, so that we've kind of whittled our way down through each of the potential income levels and therefore the corresponding tax rates. So let's go to the model to take a look at this. All right, so I'm just going to arbitrarily plug in some income level here in Model 4. Let's just say it's 42,000. So we've got some income level that I've arbitrarily chosen, and I want to know which tax rate should an income level of 42,000 be using. And so just looking at the table, we said if it's between 0 and 10,000, it's going to be 10%. Between 10 and 37, it's going to be 15%. Between 37 and 90,000, it should be 25%. So how can we do this with an if function here? Well, there's a few ways you could approach this, but what I'm going to do is basically look at kind of the most restrictive, I guess, and work my way through. So I could start at the top and work my way down, or I could start at the bottom and work my way up. Either way, it should get the job done. Equals if. So the way this works is you start off with your most restrictive test. So I'm going to look at this income level. I'm going to see if it's, let's say, less than or equal to the 10,000, right? If it is, then we know the tax rate would be 10%. But if it's not less than or equal to 10,000, it could be any number of other tax rates, right? Any of these additional 6 tax rates. So what we have to do is nest an if inside the value if false. So right in there, I'm going to plug in an if, open, close parenthesis. And what I like to do with these nested ifs, these can get really ugly really fast. So my trick to keeping them kind of structured is to jump up here inside the formula bar. If I click inside this nested if, you'll see that the formula arguments change. So now we're looking at the nested if only. So here I would then check to see if the income is less than or equal to the next one in the list, which is 37,000. If it is, we're going to use 15%. Otherwise, well, we have to nest another if. If, open, close parenthesis, and again, I'll jump up in here inside that nested if. Now I'm checking to see if the tax rate is less than or equal to the next one in the list, 90,000. If it is, we're going to use 25%. You can see already that's what's populating. But what if it wasn't less than 90,000, less than or equal to 90,000? Then we'd have to nest another if. Clicking inside this nested if, I would now check to see if the income is less than or equal to 186,000. If it is, we're going to go with 28%. Otherwise, we nest another if. You can see how ugly this is getting. Clicking inside the formula bar here, now checking to see if the income is less than or equal to 405,000. If it is, 33%. Otherwise, nested if. In this nested if, we've got to check if the income is less than or equal to 407,000. If it is, 35%. Otherwise, well, there's only one other option left, and that's that we'd have a tax rate of 39.6%. So yeah, this looks really ugly. I mean, just look at that formula. We've got, what, like 6 nested ifs here? And hopefully, when you start having these nested functions, I always kind of look up at the formula bar, make sure that your last parenthesis is black, right? These are color-coded, so it opens with a black parenthesis. It's got to close with a black parenthesis. Otherwise, it'll give you an error when you hit OK, or it might try to correct it for you, and it doesn't always correct it properly. So here, hitting OK should give you a tax rate of 25%. And of course, this should be, if you change the income level, let's say we make it 100,000, we're going to see that fall in here at the 28%. What if it's 410,000? well, then we're going to get the highest tax rate possible, right? And you can mess around with different numbers. If it were 80,000, we end up with 25%, right? If it's 120,000, we end up with 28%, just kind of messing. 200,000, we end up with 33%. So everything seems to check out with this if, even though it's really pretty ugly, and it's so easy to make a mistake with this. And that's the rationale for using this VLOOKUP, vertical lookup, as opposed to the if. So let's work through this using the VLOOKUP, right? Vertical lookup, VLOOKUP. So here what I would do is VLOOKUP. Basically there's two types really. There's the HLOOKUP and the VLOOKUP. HLOOKUP would be horizontal and VLOOKUP is looking vertically through a table, which is what we're trying to do here. So we're looking for a particular value, that is whatever income level you've plugged in here. We're looking for that within the table, and we would select this area here. Now it's key that whatever it is you're looking for, the income in this case, must be the left column in this lookup table. So that's how we have it, and so it'll work. Column index number is indicating which column within the table you want to output. So it's not the first, but the second column that we want to output, the tax rate. Plugging in a 2. Now this last piece is absolutely crucial. The range lookup. If you plug in a false here, it's going to say that we're trying to find exactly this income level. We don't want it unless it's exactly matching up. So if I were to say okay, it's going to tell me NA because it can't find 200,000. If instead I go back in and I say, well, we want to find a close match, an approximate match, we can leave it blank or put in a true. And then the way this is going to work is it's going to start at the top of the table, and it's going to keep going down through the table until it hits, in this case, 200,000 or above. So starting at the top, goes down, 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 stops right here. And then what it'll do is go back one row and output the tax rate that's applicable. And so that's how we're getting the 33%. And that's why this table has to be set up in such a way that we mentioned, like these two go here, right? These two go here, and that kind of thing. Now, the other key piece of information is the table has to be sorted in ascending order. The income on the left has to go from smallest to largest. Otherwise, you're not going to get the right answer here. Just to show you what I mean, if I were to rearrange the sorting on this, it's going to mess everything up. Here, if I said data sort, let's say I sort income largest to smallest, just to see what happens. You see, it's messing this all up. I mean, never mind the if, because that's totally off. The cell references there are now totally off. But here, it's giving me 10%. It's just not giving me the right answer. So always a good idea to spot check your results if you use a VLOOKUP with an approximate match. But more importantly, make sure that your data is always sorted smallest to largest by whatever your leftmost column is. So in this case, income, smallest to largest. Once you've got that set, the VLOOKUP should work appropriately. And again, just to try this with 42,000, sure enough, we're getting 25%, whether we use the if or the VLOOKUP. You can see how much easier the VLOOKUP was to use. All right, so we've covered quite a few Excel functions today. In the next class, we're going to continue working with some more advanced Excel functions. We'll do this for a couple of lectures before we start getting into VBA. and doing some more financial modeling with programming, VBA. So there is a homework assignment due for this module, so you'll want to be sure to look at that online. It's based on some of these hands-on examples that we worked through tonight. So for next week, you want to be sure to complete that assignment and bring it with you to class, and I'll see you then.